just so we are ready on both platforms. In that way, we'll have people joining in the Zoom session as well. So GM. Let me quickly do some settings here. I think everybody can post now on Zoom, right? Can I see a GM in the chat? There we go. We have again Armando. He was the first one for the last session as well. Okay, I think we're ready. YouTube is set up as well, by the looks of it. Yes, so we're good to go. GM, everybody, welcome to the second workshop of day 2 of the hackathon. Just a quick recap of what we did yesterday and today. So yesterday we had our kickoff call, and we had our first workshop getting started with StartNet. And in the last hour, we had an introduction to the Dojo stack. All of these recordings are available on the Biddlebox channel. So in case you missed some parts, feel free to check that out. For today's workshop, it will be about building effective AI agents with simple composable patterns. In this session, Kirill will dive into build powerful, flexible AI agents with minimal effort, leveraging simple composable patterns for effective AI and development, and much more. I'm happy to introduce Kirill. He's he's a product manager at the Nethermind team. And Kirill, welcome to this session. And I guess you can take the floor and kickstart this session.
Yeah, thank you. Happy to be here. I'm Kirill, and I've been working in the AI space since 2017. Short introduction about myself. I started as a ML and AI researcher, then managing products and teams in this space. Then in 2021, I entered Web3 space, building indexing platform based on the graph. Currently, I'm at Nethermind, and I work on various projects on the intersection of AI and Web3. Including the product that we recently released, which is called Audit Agent. It's AI smart contract auditor, and we had a few cases when it showed some vulnerabilities, some bugs that were missed by the professional auditors. Also, we are building various agents currently at Nethermind, including influencer agent, trading, and DeFi agents. So going forward to the topic, so today we're exploring building the effective agents using LLMs. And I would like to share some insights this workshop is based on the recent material from Anthropic, where the company showed their view on the patterns on how we can build effective agents. And what is interesting is that when we start using LLMs in our development workflows, we are getting the next layer of abstraction. And as in programming, we can have some effective patterns or ineffective ones. And if we know these new patterns, it helps us to make the agents easier in more reliable way. Basically getting new functionality that we couldn't get without LLMs and these agentic approaches. So one consistent observation that most successful implementations of the real world agents often aren't the most complex ones. So simple composable building blocks frequently yield better results than sophisticated frameworks. It is basically caused by the non-deterministic nature of LLMs. So every time you write something complex, you then need to make it work, and not just work, but also work in a reliable way which can be actually challenging. So usually it makes a lot of sense to test ideas of agents building the core algorithms manually, avoiding complex frameworks. So the term agent carries various interpretations. Some people are describing agents as something which is autonomous, fully autonomous. Others sees them as kind of simple workflows. So all these variations fall under agentic systems, with a notable distinction between the workflows, which follows the predefined steps, but using LLMs and still kind of agentic systems, and agents which are making their own decisions. So these differentiations help us determining the model that can be trusted with autonomous tool selection and past findings. So LLMs features naturally tend towards complexity. So the key consideration lies whether the flexibility of an agent truly adds value to the specific use case or not. So agents typically involve higher computational costs, increased latency, while also carrying a higher risk of deviation. In contrast, structured workflows often offer better predictability and cost efficiency for tasks with well-defined processes. So here is one example of whether we actually should use LLMs everywhere where we can. So just to highlight, there is a way how to not use LLMs. So for instance, to check whether one instance is one object is actually instance of the other of a class, we shouldn't use LLMs. But it's just a joke. So going forward, regarding the network frameworks. So I guess all of us are familiar with ELIZA, which made a lot of noise, and it's great because it's established some foundation for chatting agents in socials, and introduced a lot of tools that you can easily attach to the agent. But at the same time, it doesn't cover the fundamentals of building agents that are actually following your entire strategy. So, for instance, by default, what it proposes is to react with the using LLMs in some consistent way, using the long-term memory. But at the same time, when you are trying to create something more sophisticated in terms of intelligent using tools, you still need to create something from scratch. So the part which is related to how it is supposed to work with the tools and how it should avoid problems, mistakes, etc. So another ready-to-use solution is kind of agentic frameworks like LangGraph on LangChain, Microsoft AutoGen, CrewAI, and OpenAI Swarms. They provide also higher level of abstraction for multi-agent communications or using tools. And these can also accelerate the development in the beginning, but at the same time, it's hiding the details, and debugging becomes more challenging when prompt and response visibility is not it's not fully visible for you. So starting with direct LLM API calls often provides better understanding with like frameworks, and frameworks can become a valuable addition further. So we start from the understanding what is the new thing for us when we are building agent, and which is a basic building block. It is called kind of augmented LLM. It represents the model enhanced with some additional capabilities. For instance, database access or tools utilization, or some context that we are putting, some texts or some information that we are putting into the context while calling the LLM. these augmentations might include like memory of previous interactions or API integration capabilities. And effectiveness increases when these enhancements align closely with the specific problem requirements, supported by clear documentation like that enables LLM to utilize tools effectively. Going to the first pattern. First, the simplest pattern is prompt chaining. It involves breaking the complex problem into the manageable segments, with each segment utilizing an LLM call. So QA here can be maintained through programmatic gates that validate intermediate outputs. This approach works particularly well for tasks like content creation, where outline verification precedes final drafting. And here is the example of how it can look like. So it's in Python, but it can be written in any programming language. Let's review this example. So in the beginning, we are defining a client. It can be OpenAI or Anthropic or Google or something else. We define the basic function to call a model, which has an input prompt with the text, with all the contents that we are putting there, and respond with the results. And here is the how we are doing prompt chaining. So the marketing workflow example, we have an input like write a short marketing copy about the topic. Never use so short prompts because they never give you the results that you expect. But just to highlight the idea, we get the output here. Then we can do some checks. For instance, if it's too short or if the model has responded with an error. And the next call is to with the prompt like translate to. We put here target language variable and the content that we just extracted on the previous step, and we return the output. So the usage will be like we can ask to create eco-friendly water, like some kind of text about this, and to translate it to Spanish, for instance. This is the simplest way of prompt chaining. And the next pattern is routing. So with routing, we are focusing on classification of some direct inputs that we are getting from somewhere, from any type of any part of the system, and it may involve different prompts for further processing according to, for instance, the class of the request. In this case, we get, for instance, in the example, we are taking the beginning is the same, and here is the function which does routing. For instance, at first step, we are creating a prompt which is containing the default question, like to default intention to classify the input as here we use 3 types of potential requests. In the example of routing the support queries, for instance. So we ask LLM first to classify the request as a refund, technical or general. We put the query as an input, and we ask to answer with only one word. It is also not the fully desired approach because we'll need to actually this is my son. So continuing, in this case, we are asking LLM to classify the input, And in real world scenario, we would rather ask to respond with a JSON format, because if we're asking to respond with one word, there is a high probability that it will respond with one word and some extra information, like you ask answer with only one word, and it asks the one word is, and this one word that you're expecting. So it's not the way that you expect. But if you ask to respond in JSON, then you can extract it easily, even if it puts some extra information as an output. So we here in the simple example, we're extracting the category, and then according to the category, we can send some different type of prompt on the next step. Here we have handlers dictionary, where we have for refund, we have a prompt like handle refund request professionally for, and then we put this input, or for technical, provide technical troubleshooting for, or for general, some other thing. And then on the last step, we are calling GPT with the category as an input, with not the category, with the handler dictionary by default, determined by dictionary, the new prompt, and then we are asking to get the result for this query. Going further. And here is the example of how we use it. We also have a function called GPT-4 as before, and for each query, we just call the road customer query. As a result, we will get the query, the category that has been determined, and the response. Next pattern is parallelization, and here there are actually two parts of this approach. It's not just like parallelization in the programming. When we do the same task in parallel to actually perform it faster, for instance, or to so basically to finish faster. But also here are two things. First is sectioning. It means that we are dividing the tasks into the concurrent smaller components, and voting when we are running the same prompts for different parts of the same prompts for different parts of the input, or for the same input. So just to give the example of difference, for sectioning, each model does different work on the same input. For instance, model A can check the grammar of the text, model B can check the style of the text, and model C can check the facts. And then we aggregate the results. And in voting, we actually, all models do the same work, and the results are compared and aggregated. And here is an example for this scenario. We also have the same beginning, and here is the main function, not the main, the function, which becomes asynchronous parallel code review. This is example of reviewing the code. And there are three aspects for which we want to review the code: for security issues, for performance issues, for code style issues. And we start a cycle, which is actually the parallel calling of the functions. For each aspect, we are running call GPT-4 with prompt and the prompt prefix and the code. And we run it in parallel via Syncio and get the result dictionary. So here is the remaining code, the rest of the code. Here, the same function for code GPT-4, and the main function, which shows the example of how we are applying these functions for this sample code. So this sample code is supposed to be reviewed, and we run it via parallel code review. And then for each result, we have the review output. Next pattern is Orchestrator-workers. And here we are managing the distribution or the coordination, doing coordination between the LLMs using the LLM, which is orchestrating. So it's different compared to the previous one because LLM is actually doing some part related to decisions, like whether we are calling this LLM or not, or like which information we are putting, and even how many calls we are doing. So unlike the fixed patterns like prompt chaining or parallelization, it's kind of a dynamic task allocation based on needs. It's much more flexible, so we can we can solve harder problems. For instance, this flexibility in the following example, we will see how it helps to do this various scenarios related to the code analysis. So here is the example. So I will skip the part which is the same with called GPT-4 functions and the orchestrator function. So in this example, I would better switch to the end because it will be easier to explain what we're doing. So here in main function, we want to the task add input validation and error handling to all functions. And here is the input. The input for this task is the set of files with the code of files. So here are the functions in the example, but it could be files, for instance. And there is a function orchestrator code update, which handles the task and the files. And then there is a result printing the results. And now we can get back to the orchestrator code update to see how it is designed. On the first step, we actually create a planning prompt with the task as an input and with the list of files. And we don't even show the text of the files here. So, and the task, the prompt finishes with the create a plan for the file changes, respond in JSON format, like this. And here we see the desired way of using tools because we ask to respond with a JSON. It's a good pattern. And here we do this first call to GPT-4 with this input prompt. And we extract the output as a JSON. Here we also see that there isn't done any error management in place, because if the LLM is answering with some text plus JSON, it will break down this line of code. So we should rather do some extraction, assuming that LLM can answer with something besides the JSON. But here, for simplicity, we have only this, and the result of the plan will be the input that we are using for the next cycle. So when we're extracting it from the JSON, the result can be actually the list of the actions, which can be of any amount of components. So for instance, if we are putting as an input list of 5 files, then the result will contain 5 elements in the JSON, and then we will go through this cycle 5 times. In this so here we have the prompt with update file according to change description, current content, and the file name, and a file actually with the key of file name, and we're getting the text of the file, and we do task append. It's again to run it in parallel, and we are reducing it to the results. So in this scenario, as we had in this schema, the orchestrator is also an LLM, which gives us more capabilities to do more complex and flexible, to do more complex tasks in a more flexible way. The next approach is called Evaluator-optimizer. And this pattern creates a feedback loop where one LLM generates content while another one provides evaluation and critique. And this iterative process continues until quality criteria are met. And this approach mirrors the human editing process and works especially well with clear evaluation parameters. Looking at the example, we can see that first of all, it's pretty short. It's shorter than the previous one, and we have only 2 calls to LLMs. But they are done in the cycle with max iterations, because we assume that possibly the evaluator will never meet the criteria, and we don't want to go to the infinite loop. So in this task, we do the iterative translation improvement. So it's a bit artificial example. You can add some other ideas of more real-world examples where the estimation would be more clear, the estimation, the evaluation of the results. But in this case, we can show how it could work. So as an input, we are getting the target language and the text. So at first we call ChatGPT to get the translation. Then we go to the loop iterating with AI and calling ChatGPT to evaluate this translation versus the original text. And in this, again, simple example, we're asking to answer with perfect, if it's kind of perfect. Otherwise, explain what to improve. And this explain is actually important because it gives this flexibility. It gives us the potential to make something more more interesting, more complex, and solve more difficult tasks. So we, as a result, we are getting this evaluation. It's either perfect or the explanation, and then if it's perfect, we just go, we break this cycle and go to the end of the program. But if it's not, then we are calling ChatGPT again and asking, improve this translation based on the feedback. We put here the original text, they put the current translation and the feedback. So in this case, even, for instance, how it can be helpful, if the LLM that we are using is should be really cheap, then we use some that can make mistakes, and then we can, in a few cycles, we can get better quality than we would have in one cycle, and we do it iteratively. But as I said, it's a bit artificial example because in this scenario, we are, the problem is that here we could expect that the evaluation can be not so good also as generation. And it better works when you have some tool that is estimating the results. For instance, if we are generating the code, we can compile the code, and if it's not compiled, then it shows some error, for instance. Or we can run the code and get the output as an error, and we can put it back into the loop, and then it will try to fix this. And the last pattern is called agents, like autonomous execution. And autonomous systems represent the evolution of agentic capabilities. These agents begin with an objective or kind of directive and autonomously determine their path forward. Tool utilization, environmental data collection, iterative progress, they work towards task completion. And while this autonomy proves powerful, it's really powerful for open-ended challenges, but at the same time, it gives us much more opportunity, much more possibilities to go out of the correct way. So if we are allowing, let's say, LLM to decide the entire planning process without any guardrails, for instance, and the more complex task we are putting, the more probability that it will fail. In that case, the guardrails that we can write in the code explicitly are actually helpful. So we are trying to allow LLM to decide by itself in exactly in those parts where it is really needed. In other parts of algorithm, we are trying to actually reduce the amount of the amount of freedom for the LLM. And the example here, this example is a most kind of comprehensive compared to the previous ones in regards to tools usage and planning capabilities, etc. So here we define the class of minimal agent, which has tools. In this scenario, we define that the agent has 3 tools. One tool, search docs, calculate another tool, and write file, third tool. The names which the names of the functions which makes sense for us as readers also make sense for the LLM. Also, we give tool description for each tool. We explain, for instance, it's still artificial example, but it shows the main concept. For instance, for search docs, we write available arguments are pricing and features, and it returns text. So we explain how it's supposed to work, this function. Then calculate. The argument should be a numerical expression that will be executed as eval. It's a function in Python that just evaluates the numerical expression. And then the function write file, the argument should be the text to be written in the file. Then we have the same function as usual called GPT-4. And then we are defining the tools actually. So the search docs function, it's actually the function, and here we define it to simulate the behavior as a dictionary with 2 keys, pricing and features. If we call pricing, if we put pricing as an input, it will respond basic plan $10 per month, pro plan $20 per month. If it calls it calls with features keyword, it will respond with something which is not related to pricing, obviously, with some text. For calculate, this is a simple function that actually does returns the eval of this input of anything that we are putting there. And write function just simulates the writing into some file, but just responding with the successfully wrote something that has been sent to the function. Next function is actually something that is managing the execution. We have 2 functions, 2 important functions, how we execute this. First is get next action, where we actually trying to ask the LLM to tell us which command it wants to call. for instance, in this case, what we give it as an input, the task and the context. The context is changing, the task is the same, and the prompt looks like the task, and we put here the task. We send available tools and we send tool descriptions. The tool descriptions from the previous slide contain the actual descriptions with the names of the function, so it can choose from the names. And the context. The context is something that we are controlling. So on the first step, it will not have something important, I guess. And then we determine the next action to take based on the current context and available tools. Previous results will be referenced using this notation like result X, where X is a step number. It's important to explain how this context part will be arranged, because it doesn't know what's supposed to be there. So we're explaining there will be result, let's say 1, with the actual result of step 1, etc. And asking respond in JSON format as like tool name, args, arguments. If task is complete, respond with task complete, and that's it. And we are calling code GPT-4 with the entire prompt. The response, we get the JSON and we extract the output. The second important function is execute action, which is actually calling the tool according to what LLM told us. So as an input, we have the action and we have the context. I'm not sure if we need the context here actually. So the action tool, we check in the beginning if task is complete, we just don't do anything. But otherwise, we are actually taking the function, which is described here. So we get the name of the object function, and if it's not tool, we process the error, and otherwise we are returning the tool with these arguments that LLM has passed us with the chosen tool. The last function is actually controlling the entire problem. So what we do here, we start with empty context, empty results, and step 0, and run infinite cycle. Now, while true, and we do two things like as expected. We do first get next action, and then we do execute this action. We increment the step, we update the context. As I said, like for first, we will update in a way result 1 and actual result of the first iteration. For result 2, next, etc. And appending the results. And finally, the main function looks like this. We create the object of this class agent, and we can write this type of task, which is pretty raw. We ask, create a pricing summary. First, search for pricing information, calculate the yearly cost for basic plan, it's important, and write a summary to a file. That's it. We don't tell how to do that, and we call it solve the task. And here we can see how it actually works on the right side. So it's just printing what it does. Starting task, create a summary, it's just what we asked it to do. Then it shows planned action. It decides to use search docs and with the arg, which is pricing. Because if it would choose the wrong argument, it would never get the information about pricing. It would choose something else. So it decided to choose pricing. It's good. Then it got the result. Basic plan, $10, and pro plan, $20. And then it decides to do the action calculate with the arguments 10 multiplied by 12. So it's decided to choose 10 instead of 20, for instance. So it has chosen automatically that it will grab this number from the previous response and will multiply it by 12 using the tool calculate. So after that, it gets a result 120, and then it decides to choose right file and putting here at the actual $120 with some description. And as a result, it sees that they successfully wrote, and then next action it calls called task complete and task complete. So this is the fully operating agent, which is autonomous. It built on the all the like most advanced patterns that we could use with the LLM, and as we see it's really the input was really rough, not determined at all. So we can write it in other words, and it still will still work. This is just an example of how like more complicated agents can look like. This is the high level flow of a coding agent. I will not go to the details. It just shows that there's a lot of steps that should be done to make more sophisticated tasks, like coding, for instance. Coding, it means that the actual agent. And so these all, just to recap, all these workflow patterns, they are like modular components. So we can use them in any combinations. We can interconnect, alternate, nest, etc. So we can increase complexity and resolve more complicated, more problematic tasks. And we also, while we are doing that, we should obviously track the metrics, and the metrics for these types of agents are different from the program. So it can be like success rate, operational cost, user satisfaction, etc. So something which makes sense for your application. So again, to recap, several patterns have emerged from successful implementation. So simplicity often correlates with reliability. Starting with fundamental approaches typically provides most stable foundation. Transparency in agent observations enhances understanding and trust. Visibility into process steps proves valuable for both development and user confidence. The interface between agents and computational systems carries similar importance to human-computer interfaces. So framework selection also influence their reliability and transparency and complexity in debugging. So I guess that's it from my side. Here are my contacts if you're interested to like ask anything after this session. And here is the link to the audit agent that I mentioned in the beginning. You can also try it out. Thank you.
Fantastic. Thank you, Kirill. We have a few questions, I think a few more, but we'll see how many we can cover. So we can start, we'll take one from Zoom, one from YouTube, and we can get started. So the first question is from Nico on Zoom. How can we implement orchestration on Eliza?
Yeah, on Eliza, Eliza is open source, so this covers two things. First, you can modify whatever you want, so you can write your custom models. But also at the same time, it hides some particular pretty sophisticated structures from you. For instance, how it actually responds according to the prompts and persona description and using the long-term memory. So you have to dive really deep to control this stuff. So it's not easy. That's why I'm kind of partially I was not trying to describe how to work with Eliza, but how to actually write it using the patterns from scratch.
Fantastic. Thank you. Now, taking a question from YouTube from Victor. For starters, what free models can we use for the sample AI agent? I personally used some models from Google Cloud a short while ago for website analysis.
So usually you use according to the cost and performance. Regarding performance, you can open the leaderboard like on LMC's leaderboard or Sweep Bench or something like depending on what problem you are resolving. For instance, on LMCs, you can choose different types of problems, tasks, and choose, just find which LLMs are better on this task. Also, the cost is important. So, like to start, you can use, for instance, GPT-4o Mini and GPT-4o, and it's good for like most of the tasks. One is cheaper, the other one is more expensive but more precise. Also, kind of Claude 3.5 is really good with coding, and more advanced models like O1 from OpenAI, they're helpful with in complicated tasks with a lot of criteria, problems, etc. Like for instance, on auditing, we're using O1 like as a primary model. But in most scenarios, I would start with 4.0 or 4.0 Mini or Claude 3.5.
Fantastic, thank you. And I think we have a question on the task from Laura. Can the task be on-chain task, like a transaction based on the searched data?
Yeah, why not? The problem with on-chain stuff, whether we expect that the agent will be actually kind of living on-chain, it's impossible. So the agent is something which is working outside of chain, but it can work with on-chain. It can execute transactions, for instance. It can access analytics. Everything that you are implementing using this kind of tool using approach. So you write this tool, you use this tool by LLM, that works.
Fantastic. I think we can do two or three more, depending on the complexity. But one is about the track itself. So, in the requirements for the track for the best AI agent app on StartNet, it says it's mandatory to use any agentic framework. Could you give some examples of what would be considered like agentic, like eligible agentic framework?
Yeah, for the hackathon, you can use whatever you want. There's no limitations. And I mentioned a few frameworks in the beginning, like QAI, Microsoft AutoGen, LangGraph, LangChain, and yeah, here, OpenAI Swarms. Like all these frameworks are helpful to do some bootstrapping, like easy to start easier. But as like following to this all this discussion, I would avoid using them from the beginning. So the core algorithm is better to make on these approaches that I explained.
Fantastic, thank you. Do you think we can do one more or?
You told me that we should finish 3 minutes before.
Yeah, I think we can do one more. So there's two people asking about, so Anton is asking from YouTube, what challenges you faced implementing AI agents, and Flanito on Zoom asking on which LLM you spend the most time in your research and consider to have the best results. I feel like it's kind of like a combination of the two.
The challenges, first of all, the when you use LLMs, as I said, it's a non-deterministic structure which can respond kind of in different ways to the same input data. But usually we don't have the same input data. We usually have different input data. So it's even growing diversity of the results that should actually follow some expected outcomes that you want, and it's usually can start working in intentional way, and then it just works a bit different in some other data, and then you start debugging and you try to optimize the prompts to get the stable results, and it can be challenging. So you need some good data sets, metrics, etc. So all these pipeline from data science to make it work reliably. So this is the kind of main challenge. Like in audit agent, we have more challenges because basically LLMs are not good enough to do all this stuff, and we are trying to every time get a bit more and a bit more, and but it's not related possibly to the first problem, which still actual, but just outside of the capabilities of current LLMs.
Fantastic. Well, Kiri, thank you very much for answering these questions. There are a few more, but for those who want to reach out to Kirill, make sure to reach out to his Telegram or on Twitter, and you can get in touch with him and ask all of these wonderful questions. Thank you again, Kiri, for the wonderful workshop on building effective AI agents. For support on the AI track, please join the Beetlebox Discord channel. Where there we have mentors there to help you, ready to assist you and support you with any technical questions you have or even project questions. And additionally, resources and materials are available on the AI challenge page track. So make sure to check that page out. The recordings will be shared with you on the Discord channel, but also it's available on the YouTube channel of Fiddlebox. And I would like to give a special thanks to Nethermind and to Cartridge and Starkware for representing the AI agent track and for their support. And one last thing, don't forget about the special bounty from Nethermind. There's a special bounty named Create an AI-powered DeFi assistant on StarkNet, which is available on the AI track. So you could potentially combine these two tracks if you want to. That's it for this session. Up next, in
Thank
just
you.
a few minutes, we have scaffolding dApps on StarkNet, and make sure to tune in. Thank you, Kirill. Thank you for the fantastic session, and thank you for the participants for tuning in and joining in. Have a great day and stay tuned.
Thank you.